Hello? Am I here? Testing, testing. I am here. Yoo-hoo-hoo! Oh my God, I think I've done too much coffee again. Woohoo! How is everyone? Good afternoon. It's a beautiful, beautiful day here in Boston, in Cambridge, Massachusetts. Um, which is the good Cambridge, by the way. I was in the other one. It's very fancy, really beautiful buildings, all the pontooning and the canals, whatever. But you know, I like this one better. I'm absolutely joking. Cambridge, UK is beautiful, and you should definitely visit. It's a really, really nice place. Anyway, what are we doing today? Ooh, what are we doing today? Hmm? What are we doing today? Uh, Lara, Andres, Nylan. Good afternoon, everyone. Very happy to see you here. So, all right, let me center myself a little bit. We were doing Intro to Parametric Modeling. We were doing, what were we doing? We were going to do, we were here. So we were doing exercises. We did the checkerboard this morning. We did attraction and repulsion. And then today we could do a hanging cloth exercise, and I'm thinking of doing the Berlin Holocaust Memorial again. And I think perhaps this one, I would like to make it really fast. Perhaps we could do like a really summarized version of this exercise, and then say point people to watching the actual modeling challenge that we did. That was way more exhaustive, way more comprehensive. And yes, I think that could be interesting. Up to where we were in the content. Hey Albert, yeah, it's been a while. Good to see you. How are you doing? All right, well, sorry. Before, let me do a formal introduction. Wait. Sorry. 1, 2, 3. Welcome. This is Jose Luis. This is Parametric Camp. We do computational design. We do live streams. We do tutorials. We do a lot of things. Welcome. Thanks for being here. I would like to invite you to consider that if you think you're going to like what you see in this video, just subscribe to the channel, like this video, subscribe to notifications to be up to date about when we post and when we go online. We also have social media. We post when we go online there. We have a Discord channel that I'm posting. We have a Discord server that we're posting on the chat right now. And we also have a Google Calendar that you can subscribe to see what all the events that we do with live streaming. On top of that, we typically stream on Fridays, and we cover all different topics like learn how to code, computation, Grasshopper, Unity, how to do fancy 3D stuff, 2D stuff. We don't have limitations in terms of dimensions, and and then what we're typically doing is we're typically live stream on Fridays. It's just that I am halfway through recording this playlist that is called Introduction to Parametric Modeling, and I wanted to, it was one of my New Year resolutions to reach 100 live streams by the end of the year, and I'm doing really, really poorly. So because this is live stream 52, I believe we did live stream, this is 53. We did live stream 50 yesterday. How awesome is that? 50 live streams. Woohoo! All right. I think live stream 100 should be like a huge community gathering. And like just everyone meeting and talking about life and teaching and learning and all those kind of things. So I think we're going to do that. Lara, can you not see the live stream? It looks really good on my end. Everything looks, I have all these green lights on YouTube telling me that things are going fine. Anyway, so this week we're doing an intensive live stream thon, recording videos for the Intro to Parametric Modeling playlist. And this afternoon we're going to record 2 videos. As I was saying, we're going to do a hanging cloth exercise, and we're going to do a summarized version of the Berlin Holocaust Memorial because I have to go in 1 hour. I have another meetings. I have another meeting that is quite important. So yes, we will be back tomorrow all day for this one, which is super, super interesting, is super, super important. And this one, I really, really, really wanna, I really, really, really wanna do this. And I really want to take good care of doing this one because this is one of the main problems when doing Grasshopper is manipulating data. So I really want to take good care of doing that. So I'm going to do that tomorrow. Now, so what are we doing? I need to connect some Rhino here. Oh, and I need to connect my laptop so that I can do sketching. So can you give me 1 minute? I need to remote into my laptop. And I need to remote into my laptop and I need to put it here so that I can draw with you as we go. And I have all these coffees everywhere. How's everyone doing, by the way? Are you good now, Lara? Akidaki. All right. Okay. And then, so we're good here. And then I need to connect to a wireless display. That's going to be this one here. Oh, something flashed there. And then here, I'm going to move this here. I have so many things in my desk right now. Oh my God. And then I'm just going to take that and put my laptop here. I have this, I don't know if I've ever shown you, I have this fancy laptop, which is, which falls the other way around. So I can have it as a tablet here. And then I put it right here in front of me. And that's what I use for drawing. And then what I do is I open here Sketchbook, which I really want to rethink this workflow. I open Sketchbook and then Sketchbook, which is here. So I just lower it down here to my other screen, and then I can do. Maybe I want to rethink right now. Hold on. So I've been using Sketch.io.sketchpad. No, I've been using this and it was kind of nice. Oops, no. So for example, what if I did, what if I did this and then I say, oops, what? Wait, you're not seeing this? Oh, wait. Interesting. Okay, wait. So what about a display capture? Because I can't get a display capture here. Ooh, that sucks. That's what I was doing. I see. Oh, so I would need to do this. I would need to record from this window capture, which is, for example, this Firefox here. Oh, I see. I see. Well, that kind of sucks. But oh well, maybe it's not so terrible. Oh, and then I can just draw here like, hey. and then I can, the nice thing about this is that I can modify things. So I can just say, I can just move this around and, well, this is not very responsive. Anyway, I will tinker with this some other time, because obviously this, we don't want to lose time with that now. Oh, wait. Okay, that one. And then I can open a sketchbook. Okay. All right. That makes more sense. Okay, well, where was I? Yes, I was very distracted with my screen. Sorry. I can answer this week is our final exam for the diploma. Which diploma are you doing, Lara? Where is that? You were in Germany, right? Is that correct? Okay, so let me get busy. So we're going to do in the afternoon of 18.5, we're going to do exercise number 6, which is the hanging cloth, and exercise number 7, summarized version. If you want more, go to the actual AMC. Okay. Okay. So for the hanging cloth, should I use some kind of image here? Hanging cloth. Images not going to be. Yeah, these are not going to be helpful, basically, because this is not the kind of hanging cloth that I'm looking at. Okay, I will explain it. I will explain it in the diagram. Okay, so let's get started. Should I draw? Should I draw a sketch? Let's draw a sketch first. So what we're going to do is we're going to have some kind of curve and some kind of curve here. That's going to be one thing. And then what we're going to do is we're going to just have some kind of surface that it looks like this. And maybe something like that. And then when we actually draw it, so when it is time to do the design, so we can do is we can have, oops, let's have, why is, no, because it was this one that I usually use, right? It was this one. So we have this one, and we have this curve, for example. And then what we can do is, the next step is going to be to subdivide this into a bunch of points. So that's going to be 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. And then the next step is going to be to join those with curves like this. Something like that. And then after that, what we will do is we will create a surface that goes something like this. Okay, for example, that's going to be our that's going to be our process. So I'm going to turn this on and on and on here like this. and let's discuss this. So, all right, let's do this. Exercise, we're doing an exercise. It's going to be a piece of hanging cloth. Okay, let's do this. Wonderful. Let's get started. As usual, we're going to do some sketching and some drawing to think through the process and then try to figure out the steps that we're going to follow to generate the geometry of this hanging cloth. As we said before, the hanging cloth is going to look something like this. It's going to be a piece of fabric that is somehow going to be draping, elastically or not, from two boundary conditions that are going to be the edges. So I think for me, in this exercise, it's going to be important to start with some kind of input parameters that is going to be the edges of that piece of fabric. So the shape of the two boundaries that are going to be holding this geometry, holding this piece of fabric together. And the way we can approach this problem is that what we want to do is we want to end up with some kind of surface here, right? We want to end up with some kind of surface here that kind of follows the logic of some kind of draping mechanism, or like the physics of a fabric just being affected by gravity. So if that's the case, what I can do is, for example, I can generate a surface that is going through a lot of curves. So I can generate a loft surface that is going through a bunch of curves that are joining these two edge curves. And the shape of each one of those curves, in order to make it perhaps a bit more physically accurate, I can actually use what's called catenary curves. And catenary curves are curves that have the shape that is very close, or that is physically accurate to the shape that a chain or any piece of thread or basically any linearly elastic element would have if under the weight, if under its own self-weight affected by gravity. So if I take a chain or a piece of rope and I hold the two extremes, the shape that it deforms under, with no additional weight, just its own self-weight, under gravity, that shape is typically called a catenary shape. And there are mathematical models that describe that shape very accurately. So what I could do is I could say, for example, the process that I'm going to follow is I'm going to start with my two input curves. Something that I could do is I can subdivide each one of those curves into a control amount of points. So how many points may also be a parameter in my definition. And the more points I have, the more defined the surface is going to be, but also the heavier. So there's always got to be like some kind of balance there. And then once I have that, I can probably draw catenary curves between between the points in each one of the two sides of the curves, each one of them having a particular length or affected by particular gravity, which could also be part of one of my parameters, the length of each one of those chains and how strong the gravity is pulling up or is pulling down. And then last but not least, once I have those curves, what I can do is I can just trace a surface that lofts through all those curves and generates this napkin sort of hanging fabric kind of situation. It may not be physically accurate, but it's going to be very close to the actual shape that a fabric under these forces will have. So with that, I think we're probably ready to start taking a look at how to implement this using Grasshopper, for example. All right, let's do this. So I'm going to switch to here, and then I'm going to save this file. I'm going to put some bifocals here. I'm going to save this file, and it's going to be E6 hanging cloth. And then here, I'm going to have my viewport. Okay, so let's do this. And probably I want to save this as well. All right. Let's start by the basics. As we said, our input parameters are going to be two curves that I'm going to have in Rhino and that I'm going to bring into Grasshopper. So I'm going to draw one curve here. So that's going to be one of the edges, for example, and the other one is going to look something like this, for example, so that the shape is not exactly the same, and we have a little bit of variability. And actually, you know what? I'm going to move this a little closer here. I don't know. We can probably play with that later on. And then I'm going to bring the two curves here into Grasshopper. So I'm going to look for a curve empty parameter, or I can just do that here under geometry curve. I can drop this here, right click and set one curve. That's going to be the left one. And then I'm going to drop another one and set the other curve, the second one here. If I drop some panels here, you can see that I have the curve here. It's a planar curve, it's another planar curve. They don't need to be planar. We can change that later. All right? Okay, well, then another parameter. So that what we said before is that now what I need to do is I need to subdivide each one of those curves into a bunch of points. So I can do that by going back to, we have seen this component before. I can go to curves, division, divide curve, and then I can drop that here. And then I can plug this one, and then I can drop another one. We're going to do two separate ones, and then I can drop the other curve into the other one. And of course, right now it's dividing into 10 segments just because it's the default. But if I actually want to control that, I can just double click and drop a slider here. And a shortcut to using sliders is actually that if I just type a number, so for example 20, it will create a number slider going from 0 to 20. So actually going from 0 to the largest multiple of 10 for that number. So anyway, so I can place 20 and 20 here, and then I can now play with how many curves are going to show up here. All right. Okie dokie. So that's great. And then the next thing that we need to do is that we need to join these two families of points with curves that follow a catenary logic. I'm offering these suggestions because I know it's part of what Grasshopper can give you. But if you had other ideas, we can totally do other types of curves. So for example, if I go to spline, to curves spline, you can see that all the way down here, there is a catenary chain between 2 points component. If I do that, I can place it here. And let's take a look at the inputs. This is a really good thing again to do as practice. So A is going to be the start point, B is going to be the end point, L is going to be the length of the catenary chain. So that has to be longer than the distance between the 2 points. And G is going to be the direction of gravity. And you can see that the hex icon is an arrow, which if I go here and I take a look at what arrows are, it means that an arrow is a vector. We haven't really seen vectors yet. We will see them very soon down the list. But long story short, a vector is basically a direction in three-dimensional space, kind of. So we will be able to work with that. So let's start simple. So let's add here the starting points of the catenary. So that's the first family of points. And let's add to this, the second family to the input B. And you're going to see that something weird is going to happen, which is that, well, first of all, we don't get any curves because we are not feeding in the length component. So let me create here a component, a slider. So I'm going to type just 100 as a number, and you see that I get a slider right away from 0 to 100. So I'm going to place 100 here as the length, okay? And you can see that immediately I get all these catenary curves. And if I reduce this, you can see that, as I said before, something weird is happening. So if I look from the top, you can see that the curves are crossing, okay? Which is probably not what I wanted. I wanted something more in the lines of from one end, from the start end, from the same start end to the same end end. That was a terrible way of saying it. This is because I did it on purpose. When I drew this curve, starting from here, then throwing interpolation points here and ending here. Whereas when I drew the second one, I started with the end start point here, and I started drawing this way, and I ended here. Therefore, what happens is that the internal direction of where the curve starts and where the curve ends are actually in opposite directions. So the first point of the division is this one for this curve, but the first point of the division is this one for this curve, because this is the start point and this is the start point. So because the start points are in opposite directions, this is why I get this effect. This is very simple to solve. I could, by just simply flipping the internal orientation of one of the curves. I can do that by modifying the curve directly in Rhino. So I can just click that curve and type here flip, right? And then as I do, the internal orientation is flipped, so the start and the end points flip. And then now I get an order list of a much nicer distribution of the curves. If for some reason I couldn't do this in Rhino and I wanted to do it in Grasshopper, that's also a possibility. So I can just go here to curve, to utilities, and to flip curve. And what I can do is I can just flip one of the curves, and then that flip curve, I can just feed it into the other component. Okay, so that could be one way to go about this. And I'm just going to expand this here, and I'm going to shorten this span here. And I want you to notice how, because all the chains have the same length, the ones that are joining points that are closer to each other have a longer sag, whereas the ones that are joining points that are farther away have a shorter sag here, which kind of makes sense for a fabric that would have the same distance between the two ends of the curve, right? So I think this is a really interesting example. And then once I have my family of curves here, so you can see that the output of the catenary is a bunch of curves, right? So what I can do is I can now say, well, let's loft a surface across all of these curves. So I'm just going to go to surface, I'm going to go to freeform, and in freeform I can find loft. If I drop this here and I don't care much about the options, okay, then what I can see is that the result is this surface that is giving me that is going through all these curves. And if I disable the curves and the points, I can see that I have a very clean kind of surface that has that feeling of a hanging cloth. The last thing that I would like to do is, we haven't really seen vectors yet, but if you remember, the catenary had the direction of gravity, which right now, if you look at the component at the input, says 0, 0, -1, which means that its gravity is a vector that is going in the negative z direction. So it's pointing down. But actually, we can change that. So we will see this very soon, but I can create, for example, a vector out of x, y, z components. All right. And then for the x, I can keep 0. For the y, I can keep 0. But for z, I can just add a number slider that is going to go from, for example, from -10 to +10. Okay. And I'm going to plug this here. And remember that this was at -1. And actually, let me rewrite this so that it's from -1 to +1, just so that it's not too crazy. So we have here now a vector that is 0, 0, -1. So if I plug this here into gravity, we have the exact same thing that we had before. But now if I modify this vector and instead of making it -1, I start increasing it positively, and I move it all the way to +1, you can see that now the direction of the vector has shifted and is pointing up, which means that we're doing some kind of like anti-gravity sort of situation. And therefore, in this case, I have this surface that could be perhaps, I don't know, a pavilion. And if we made this pavilion with stone, because stone is also a material that is really good at like self-weight, so this form could actually be pretty good structurally for such a pavilion. There's many other things that we need to take care of, but it could be a good prototype, a good proof of concept. This is very similar to the process that actually Antonio Gaudí, the Spanish architect, used to follow for designing his structure, like the Sagrada Familia, and many of his like really interesting architecture from the beginning of the 20th century. So yeah, so this was a really simple model on how to create a surface that has some physical draping kind of catenary logic. Do I want to say anything else about this? I don't think so. So that was great. And now if you like this video, please consider liking the video, subscribing to the channel, all those things. And then I think we're going to do one more hands-on exercise in the series, Introduction to Parametric Modeling, before we go back to learning more concepts, okay? Thank you very much. See you in the next video. Saeed, thank you, sir. I don't have much energy left today. I'm trying as much as I can. Thank you. Ashley, do we know each other? Have you been here before? Welcome to the channel. Good to see you. Okie dokie. Oh, awesome. Welcome. So if you're first time here, you may want to look at the links in the chat and join our Discord server to have offline conversations during the week and get to know when we go live and blah, 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 and all those things. But welcome to the channel. Okay, so I'm going to record the introduction to the tutorial now, which I'm going to say, yes, which I'm going to do is I'm going to introduce just the exercise, okay? Hi, this is Jose Luis, and welcome to another hands-on exercise on this series, Introduction to Parametric Modeling, in which I'm going to model I'm going to model the logic of a hanging piece of fabric. And I'm going to do that by having the two edges of this piece of fabric, and then I'm going to create a bunch of curves that have the catenary logic, so they sag more or less depending on the length and affected by the gravity of the environment. And I'm going to model a loft surface among them, simulating more or less the physical effect that gravity would have on a piece of flexible fabric that would be hanging. And I'm also going to show you a little bit how we can modify the gravity so that instead of pointing down, it can point up, and maybe this object, instead of being now a piece of hanging fabric, can be perhaps an architectural canopy or some kind of, I don't know, some kind of built form in 3D. I don't know. So this exercise is going to be super simple. We're going to learn a little bit of more geometry, more curves, but it's going to be like a super simple exercise. Let's take a look at how to do that very briefly. All right, that was it. So I'm going to save this exercise. I'm I'm going to group this. I'm going to group this. And I'm going to group this here, put this here. Okay. That's going to be the hanging cloth. And this is going to be the... I forgot to move things around. That could have been nice in the video. Oh well, I'm not going to record it again. Okay, so we had we had the hanging cloth, so that's done. And now we do want to do Berlin Holocaust Memorial. I really want to do this exercise real quick. So what does that mean, actually? What does doing it really quick mean? Because I do have this exercise already in the algorithmic modeling challenges. So here in the challenge, we have algorithmic modeling challenges, and we have the Berlin Holocaust Memorial. We have it here. Yep. So, and it was like a longer exercise. Hmm. Hmm. And how did I do that? How can I do this so that it's simpler than the exercise that we did before? How can we do that? Huh. Okay. JW, which level of mathematics do you think is minimal for computational designers? I think if you can add numbers, subtract numbers, multiply numbers, and divide numbers, I think you're good. Well, sorry, I take that back. It would really be helpful if you had some idea of trigonometry and sines and cosines and the Pythagorean theorem. But I think that's literally all you need to start going. I don't think you need calculus. I don't think you need complex algebra. I don't think you need any of that unless you want to get like really specialized or like hardcore. Yeah, I don't think you need any of that. Okay. So I'm going to do an oversimplified version of this exercise. So of the Berlin Holocaust Memorial. Okay. So which image can I use? Do I have some kind of bird's eye? Yeah, this one. Okay, I think I can probably use this one. Mm-hmm. Mm-hmm. Okay, so I'm going to save this, and then I'm going to create a new one, new empty book, and then what I'm going to do is I'm going to explain the process really simple. I'm going to start with a surface. Okay, and then actually let me start with a different surface. Well, that is a terrible surface. I hate that surface. Whoop. And then here, and then this one. So now that's one layer. The next layer is dividing that into points. So for example, point, 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 point. Now here and here. And then what I can do is I can now project those to the ground. So that could be this, 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 and this, this, this. Whoa, that's going to be really bad. It's going to get messy. And then I could create the centers of new points here at the base. So that could be a new grid of points. And then once I have that, then I can create rectangles. I can create rectangles, center in each one of these. What a terrible drawing job I'm doing here. And then once I have that, I can make sure that I use the original distances. I don't want to do that. I want to make sure that I use the original distances to the surface to extrude new cubes, and then the new cubes are going to look something like this. Oh no. And then, wow, it's getting really messy very fast. Wow, this is a terrible sketch. Everyone, please don't blame me. Oh my god, this is so bad. I'm going to need to hire a professional, someone to help me draw these sketches, because this is just getting out of control. This is absolutely out of control. I don't know what I'm drawing anymore at this point. Whew. And here, and then here, and then here, and then here. And then when I turn this off, wow. I mean, is it that bad? Hmm. What if I do this? Am I just gonna make things worse? What if I turn this off? Oh, yeah, it's really bad. Oh. Oh, God. No. I'm missing a line here, a line here, a line here, this one here. Oh, God, this one here. My friend Nono would kill me for this. He's super into sketching. He would not approve of this. He would really not. No, 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 no. He's gonna call me out and be like, Jose, what are you doing with your life, man? Oh God. Okay, so we start off with this. So we have the surface, then we subdivide into points, we project those points to the ground, we create new points, and then we find rectangles, then we extrude those rectangles, and then boom, we get that. Yoo-hoo! Maybe I can keep this. That could be nice. I can keep that overall there. I'm going to take a screenshot of myself. Ta-da! Wait, let me do it. Ta-da! No, just ta-da! This is really terrible. Okay, I think this is what we're going for, folks. This is what it just happened. This is what happened. All right. So the video is going to be an introduction that I will record later, and which I will use to where I will show the variability of the model, etc., etc. And then here I'm going to explain the process. So here I'm just going to start by saying, well, if we want to achieve this shape, we're going to start with a surface, and that's going to be our input because we want to be able to control the surface and be like, I have like a really nice control of the surface, pulling the control points, etc., etc. And then after that, what we're going to do is we're just going to divide the surface, etc., etc. And we're going to divide the surface, etc., etc. And then we're going to project, and I will explain the process that we're going to follow. Okay. Okay. let's do this. I have to do this in less than 30 minutes, so I'd better hurry up. Okay. All right, let's do this. All right, let's do this. So just a quick reminder that this version of this exercise that I'm going to do is oversimplified and it's taking tons of shortcuts. If you want to see a more in-depth, more systematic approximation to the original monument, please make sure that you check the algorithmic modeling challenge that I referenced in the introduction, okay? But for this one, because I just want to do something really easy, like a really quick prototype, the way I'm going to approach this exercise is going to be the following. I would like to start with a surface in 3D. I'm going to imagine that I am the person who is designing this monument and that I want to have some kind of, I want to use this tool as a way for me to find what is the really nice shape of the blocks and the curvature, etc., etc. So that's why I would like to start as an actual surface in Rhino as the input parameters, because I will want to play. Once I have the design ready, all the algorithm ready, I will want to play with the control points and drag things around, etc., to play with the geometry of the surface and find the ideal shape for the blocks, etc., etc. So that's what I'm going to use as my design tool. And then the process that I'm going to follow to generate the blocks for this monument is going to be as follows. What I'm going to do is I'm going to take that surface and I'm going to subdivide the surface into a grid of points. That grid of points is going to be at regular intervals in the U direction of the surface and in the V direction of the surface. If you remember from previous videos, we talked about how surfaces, nerve surfaces, have an internal direction, have two internal directions, and we can subdivide them into equal parameter lengths. Then, once I have all those points in 3D space, I can do a very simple operation of taking all those points that will have X, Y, and Z coordinates, and then projecting them down to the ground, if you will, by basically taking all those points, deconstructing them, and creating new points with the same X and Y, but with the Z height being all at the same level. So for example, the value of 0. If I do that, then I will get basically a copy of all the points that I had on the surface, but projected to the ground, because all their Z coordinates are going to be 0. Once I have all those points down in the bottom, then it's going to be super easy to just basically create some kind of primitive shape. So for example, a rectangle on top of each one of those circles, centered on top of each one of those circles. The rectangle will be the footprint of the block, and that the dimensions of which I can control parametrically. I can have sliders, the width and the height of the block. And then after that, I will want to extrude each one of these blocks in a way that it creates a cube, but each one of the heights of these blocks will have a different height, and it will have a different height that will correspond to where it was on the three-dimensional space. So what I can do is I can actually extrude each one of them with the direction of how high it was in the Z axis. That will give me, I can calculate all of that. It's numbers that I will have as part of my parametric definition, and then I can then extrude each one of them into different blocks, giving me something like this. I apologize for the quality of the drawing, but you know me. I am not much of a sketcher. No, Martinez Alonso would do a much better job than I have done here, but you get the point. Each one of the blocks will go higher or lower depending on how far it was, the base, how far the base was from the surface, and therefore all the blocks will end up recreating that curvature of the original surface. All right, so I think these are the steps that I'm going to follow to do this exercise. It's going to be actually super simple, but again, if you want a more in-depth, more detailed, and more faithful exercise, that faithful to the original monument, make sure to check the algorithmic modeling challenge for the Berlin Holocaust Memorial. So let's do a quick prototype following these steps inside of Grasshopper, in our case. Alrighty. Can you folks please give me some thumbs down to this sketch? Because I am not very proud of it. All right. let's do this. Okay. Let's start from the beginning. I'm going to have my rhino here, my grasshopper, and then the first thing I would like to do is to create the surface that is going to be the input to my monument. So I'm going to use the technique. I'm just going to go to the right view of the screen, and then here I'm just going to create a curve in 3D space, like something like this, for example, and then I'm going to create another one, and I'm going to snap the ends so that it's more or less square in the footprint. So what I'm going to do is I'm going to start from the same point, but now perhaps the curvature, if you will, is going to be a little more pronounced. All right, but they both start and end on the same place. I'm going to go back to perspective, and then I'm going to move this curve in the y direction to create a surface that is more or less square. Not really, but it doesn't really matter. And then what I'm going to do is I'm going to type loft, and then I'm going to loft this curve and this curve together. And therefore, I will be creating this kind of surface in 3D. If I right click here and I type and I go for ghosted, I can see this other representation that is a bit more. And you can see that I still have the curves that I'm going to delete, I have the other curve that I want to delete. And if I click on my surface and I press F10, the control points of my surface show up. And then potentially in the future, I will be able to play with those control points to modify the surface of the curvature and make it more bulgy, less bulgy, etc., etc. But I will do that perhaps by the end. So maybe in the meantime, I'm going to do this. Yes, so that I can have something like that. All right, I'm going to call this my design surface, because again, it's going to be the one that is going to be driving the shape of my monument. And I'm going to bring that into Grasshopper by creating an empty surface parameter box. So that's going to be surface here. I forgot to put some bifocals here. For those of you who are still not using icons, please switch to icons. Trust me, it will be good in the long run for you. And then I'm going to right click here, set one surface, and now I have my surface here. And I'm going to drop a panel, which I'm going to be using to keep track of things. Now, the next thing that I want to do is, if you remember, I want to subdivide my surface into a grid of UV points. The way I can do that is by going to surfaces and going to utilities, and here I can see a component that is divide surface and surface frames. So the divide surface generates a grid of UV points on a surface. This is very interesting. I can see that the input is the top of the surface that I want to subdivide, and U and V are the number of segments in each one of the directions. So I'm going to plug here the component, and you can see that immediately I get UV subdivisions, and then I'm going to drop here, for example, I'm going to type 20 so that that's a little too much. I'm going to type here 10 so that I have control about how many subdivisions I have in each direction. So 10 and 10, and therefore I can now control this. All right. Just a quick note, if you remember from where we were talking about surfaces, I remember how I was telling you that UV, that the parameter space in a curve and in a surface may not be equally distributed. So you can see very clearly here in the top view how the parameter space is more dense here and is less dense here, which means that the distribution is not going to be perfectly orthogonal, perfectly perpendicular on plan view. This is also very clear to see here how the curvature here, because of the distribution of the control point, you can see that the control points are closer here and they're more distributed farther apart. That's why there is a larger distance here and here, but the points in this area, for example, are more concentrated. So this is just to say that UV subdivision will not give you points that are equally distant in Euclidean space. They are equally distant in internal UV distance, but that may not have a constant rhythm in Euclidean world coordinates. Okay? So that's why I was saying before that this is a little bit of a shortcut, because in the original monument, the blocks are actually distributed orthogonally in a grid, which is not going to be the case here. But anyway, just an approximation. Wonderful. So now we can play with how many blocks we have in each direction. And then we can see that the outputs of this component are the points that we are getting. So that's going to be all these points here. And we are going to see very soon why there is like these categories here and why they are subdivided in kind of groups. We'll see that very soon in the next coming videos. And you can also see that the outputs are the normal vectors to the surface on those points and where those points are in the UV space. So in coordinates 0, 0, 0, 7, 0, 14 in each one of those directions internally. So but these are the X, Y, Z coordinates in world space. So the next thing that we wanted to do was to project those points to the ground. And what we were going to do about that is just basically take all those points, take the X, Y coordinates and create new points at 0, Z with the same X, Y, Z, with the same X, Y. So let's just do that. I can take all those points, and then what I'm going to do is with vector point deconstruct, I'm going to extract the X and the Y. For example, these are all the X's, these are all the Y coordinates of each one of those points. And then I'm going to create a new family of points that is going to take the same X, the same Y, but Z is going to be 0, which is the default that we have here. So you can see now how I have created here a new family of points. If I compare this, I have the same points, but if I compare this with what I have right here, you can see that I have the exact same points with the exact same X and Y, but Z is now 0. So this is all the points here at the bottom. Wonderful. We are very close to done. So now what is the next thing that we want to do? Well, if you remember, the next thing that we want to do is now we just want to draw the footprint of our blocks. So how are we going to do that? Again, we're just going to find, for example, a rectangle component. The rectangle component is going to be somewhere in curves, and it's going to be under here, rectangle. And then I can place rectangles that are going to be, the base plane is going to be P, and then X and Y are going to be the dimensions of the rectangle in the X and Y directions. So this is going to be here, and then I'm going to set here values for the width of the block. So that's going to be, for example, let's say there's going to be a slider with 10 units and another slider with 10 units. One is going to be X and the other one is going to be Y. And these are super big, so I'm just going to make them much smaller. All right. And you will notice that the rectangles that I am drawing are drawn from the corner. So the point is the coordinates of the corner. This is because the rectangle component takes X and Y. It doesn't take a number. It takes a domain, which is a range between two numbers. And because I'm just giving it one number, basically it does from 0 to that number. And that's why the rectangle is offset to one side from this point. Is there any way that I can generate a simple center rectangle without getting into domains, which I want to get later on in these videos? Let me take a quick look. How did I do this in the past? Box rectangle, base rectangle. Box 2-point, center box. Yeah, but this was just, this was in the two directions. I don't want that. The main box. This one. Mm, yeah, I don't think there is. Okay, we're just going to leave that like that. But you know what? Maybe I can just explain domains. Is that not a terrible thing? Why not? Maybe we can do it. Yeah, why not? All right, let's just do it, actually. So I couldn't find one, so I wonder if I can just explain domains real quick. So let me go back to the problem. The problem is that this rectangle component, for the dimensions in the x and the y, you can see that the hex icon is indicating us that is this thing that is like a bar with two ends. If I look at my my primitives, you can see that this is what's called a domain. And a domain is just basically a range of between two numbers. So instead of saying 4, you say from 0 to 4 or from -4 to 4. So the idea is that this is asking for a domain so that it knows how to center the rectangle in each one of the directions. And because I'm giving it just one number, not a domain, it converts that automatically to a range, a domain that goes from 0 to the number that I gave it. So if I want to actually center my rectangle on top of that point, what I will need to do is basically I will need to create a domain that instead of going from 0 to the width of the box, what I would need to do is to create a domain that goes from minus half of the width to positive half of the width. So the way I'm going to do that is, first of all, I'm going to create a domain by going to the Math tab and going to the Domain category. And here you can see that you can construct a numerical domain with the two ends, given the two ends. So I'm going to create one here. A is going to be the start of the domain and B is going to be the end of the domain. So what I'm going to do is I'm going to type here expression component. That is going to be whatever you'd say, give me minus x divided by 2, whatever you give me. And then I'm going to plug that in here, and then I'm going to copy paste a new one, which is going to be the same but in positive. So that's going to be, now if I plug my panel here, you're going to see that from 1.5 whatever, or from 2, what I get is a domain that goes from -1 to 1. And let's see if I plug that into x, you can see that now in the x direction, the rectangle is centered. So the only thing that I need to do is I just need to copy and paste this and do that for the y direction as well. And then feed that into the y component. And therefore, now my rectangles are perfectly centered on top of the base points on top of the base points. All right. Okay, so that was not very difficult actually. So domains, again, domains are just basically an interval between two numerical extremes. As simple as that. Now, the last thing that I would like to do is I would like to take all of these boxes and extrude them or create an actual box that is as high as the C of the original points that were on the surface. So how can I do that? Well, there are many ways that I could do this. I could, for example, take the freeform component, and I could extrude. What is extrude? I could extrude this. I could extrude this in with a direction, which could be a vector in the C direction. For example, I could do this, and then I could just do a vector, a C vector that is multiplied by the height of all those points. And then I could have that. The problem is that this will not work great for rendering because the extrusion doesn't cap the ends. So I'm actually going to use a different technique, which is going to be, I'm going to create cubes here under primitives. There's actually one box that is very convenient in this case, which is a box that is defined by a rectangle, which I already have, and by a height, which I also have. So I'm going to place that here, and you can see that the input is the base rectangle. I already have this here. And then the height, instead of being 0 to 10, is going to be 0 to the C height that I have for each one of the points. Remember that each one of the points had a C height, and then therefore now you can see that all these boxes are closed, and that each one of the boxes at the center is actually showing here, and it's tangent. It's not tangent exactly, but it's coincident with that point on the surface. And what's beautiful about this now, as usual, because this is parametric design, because all the relationships are parametrically bound to each other, what I can do is I can modify the original surface. So for example, I can just move it anywhere, and then all the blocks will move correspondingly. I can press F10 to turn on the point cloud, and then decide, I want this point to be much higher. Whoa, so I'm going to create a larger bulge here. What other points? So for example, I want this point, or this point here, I want it much lower. So I want to create like some kind of curvature there. So you can see that now I have some curvature here. This point is also going to go down. So I'm just going to decrease this, and maybe I went too far with this one. And then you can start iterating, and you can start refining the overall shape. I can actually hide this. I can just click it and type hide in Rhino, and then this will hide it. And then whenever I think I'm ready, I can just go ahead and go to the boxes and right click, type bake. I'm going to group them so that I can move them together as a group. All right. And now I have my geometry inside of Rhino, which I can move. And then, for example, if I choose right click, render, I can do this like ambient occlusion kind of representation, and I can see what the boxes would look like as a monument, for example. And I could now send this to my colleagues, to the competition. I could do some renderings. I could do whatever I wanted with this right now. So, hooray! This is parametric modeling. And this is a bit more of an interesting example of the things that we can do with algorithmic modeling by just simply creating the chain of relationships that define a particular geometry. And again, I can keep iterating here. I didn't touch this, but I can say I want the blocks to be a little smaller, but I actually want to have many more of them in every direction. Now I'm going to make them a little tighter, a little blah, blah, blah. Ooh, they're overlapping here, etc., etc. You see, I can work. Let me bake this one. So I'm going to bake them, and then they show up here, and now I can compare it to my previous iteration, and I can see them back to back and be like, this one is too big, this one is like more. So I can make design decisions and really iterate real quick over different versions of my geometry, which is, again, like one of the fundamental powers of parametric modeling. Once you have established the relations between all the geometry entities, then iterating and seeing different versions and different examples becomes as simple as just changing some sliders or pulling up and down the surface, the input surface. So I think this is where I wanted to end today. So hooray! This was the Berlin Jewish Holocaust Memorial Museum by Peter Eisenman. Is that it? Is that what we're doing? Yes, I think I'm going to wrap it up. Thank you very much. If you like this video, please consider subscribing to the channel, liking the video, turning on notifications. And also remember, if you want to see a more advanced version of this exercise with more details, more in depth, and much more faithful to the original monument by Peter Eisenman, make sure to check the algorithmic modeling challenge that we did, which should be popping somewhere here, somewhere on the screen. And make sure that you do that. And also, if you're interested in C#, we actually did this typing it in pure code in a C# script component in Grasshopper. So it could also be interesting if you are at a more advanced level in learning how to do these things yourself. Okay? Thank you very much. And let's move on into the Introduction to Parametric Modeling series. And let's keep learning more stuff to make even better and cooler things. Thank you very much. See you on the next video. You could have used circle and bounding box. Why are you yelling at me, Parikshit? Don't scream, please. I guess I could have, yes. I don't know. All right. So I'm going to go wireframe. I'm going to show all. And then I'm going to hide and hide. I know you're not. Don't worry. Okay, I need to remember to say that this is what I want to do. I need to show it working, and then I need to point to the video. Okay. Okay. Hi, this is Jose Luis, and welcome to a new hands-on exercise on the series Introduction to Parametric Modeling. In this one, what we're going to try to do is replicate an architectural landmark, the Jewish Holocaust Memorial by Peter Eisenman in Berlin. It looks something like this, and the way we're going to do that is that we're just going to create a very simple definition that starts from a surface representing the undulation of the blocks, and then we're just going to conform a series of operations so that we end up with each one of those blocks. And imagining that we're going to be the designers. Because it's going to be parametric, then we will be able to control how many blocks we have in each direction. We will be able to control the size of the blocks in each direction as well. And we will also be able to control the input surface, so that if I just modify the surface like this or like this, then the shape of the blocks adapts dynamically. This could be a really interesting exercise because it showcases the power of parametric modeling in the case of when you design your whole parametric set of relationships, then doing quick iterations about how different versions of more blocks, less blocks, more width, less width, how this could affect your design and help you reach, for example, different iterations of design so that you could decide which one looks better, which one looks worse, and which one is going to go the one that is going to be the one that goes to the competition, the one you sell to your client, etc., etc., and help you make design decisions. So this exercise that we're doing in this video is going to be an oversimplified version of the actual original monument, because I want to use it as an introductory exercise in the Introduction to Parametric Modeling series that I'm working on right now. So this is catered specifically for people who are beginning and are still learning the basics of algorithmic modeling. If you are interested in a more comprehensive, detailed version of this exercise, or if you feel you are at a more advanced level, I highly recommend that you check the exercises that we did previously on our algorithmic modeling challenge. And actually, fun fact, these three, the algorithmic modeling, the Berlin Holocaust Memorial, were the very, very first videos that we recorded in this channel in Parametric Camp. But these three videos are a basic version. Then version 2 is a more advanced, very detailed version with many of the original details in the monument. And the third one is the same as the second one, but implemented in C#, in purely scripting, if you are interested in those kind of things. Okay, so let's take a look at how can we implement this, a simple version of this exercise in with parametric modeling inside of Rhino and Grasshopper. Let's take a look at that. Hooray! Okay, so we are done for today. I have to jump to another meeting at 3:30, so I apologize if it was a little short today. Okay? Any questions, comments? I have a couple minutes before I have to jump off. Okay, let me save this stuff. While if you have any comments or you want to chat about anything, so here, and then here, I'm going to save this. Going to be what? E7. That's going to be E7 Berlin Memorial. And then what are here? I'm going to save this as E7 Berlin Holocaust Memorial. I'm going to disconnect from here. Oops. Uh-oh, I think I'm... Oh, okay. Any comments? Any questions? I have a little bit of time for social before I need to jump off. Well, otherwise, if you don't have any comments or anything you want to chat, thank you very much for being here. As usual, I appreciate the company and of being able to do this with humans on the loop. I'm very grateful to have a community of people that are interested in the work that I do and in the things that I want to share. And just want to say that we're going to keep doing this all week. So tomorrow we will have 2 more live streams at 10 a.m. Boston time and at 2 p.m. Boston time. And we're going to continue with these exercises and increasing complexity and learn more stuff. Tomorrow we're going to be talking a lot about data in particular. So that would be super, super helpful if you are at a beginner/intermediate level where you still don't have you still don't have clarity on trees and branches and lists in Grasshopper and all that kind of stuff. So that would be really useful tomorrow will be really useful if you're into those things. Oh, and it looks like I have to jump to my other call. Thank you very much. Have a good one. Bye-bye.